Okay.
This is a Frontiers of Parameterized Complexity seminar, and our special guest today is Vincent Cohen-Adot, who will speak on parameterized complexity of clustering. Welcome, Vincent.
Thanks. Thank you very much, Fedor, for the introduction and for the invitation. I'm very happy to talk to the parameterized complexity crowd. And I'll be happy to take questions and try to stop here and there to if you have any questions. So feel free to ask at that time. But for now, I'm gonna start. So I'm gonna try to give you some ideas that we use to solve some of the clustering in FPT time, some of the famous clustering problem in FPT time. What are the main open problem? But in fact, I think this talk is also a way to try to get more people interested in coming and solving this clustering problem in FPT time, and to try to highlight some of these clustering problems so that we can get more answers to these questions. All right, so there are two types of clusterings that usually people look at. There is the first clustering, which is the metric clustering, where the input is going to be a set of points in a metric space, and we would like to partition this metric space into clusters where points that are close end up in the same cluster, points that are far in different clusters. And the standard example here is the one of the thing I give as exercise to my students is like points in RD. Each point represents some object. Here it's like maybe an image that represents some handwritten digits, and the distance in the Euclidean space represents the how much the images are similar. So if you pick two images that represent the same digit here, two images that represent the one, they're going to be very similar. If you take the L2 norm between the vectors, between the images, and between a 1 and a 8, maybe they're going to be very different. So the distance will be higher. And so what you want to do is find groups that of points that represent the same image. So basically points that are close to one another in the Euclidean space. Okay, so that's one type of clustering, and that's more or less what I'm going to focus on during this talk. But there is another one. And also there are a lot of open problems for the other version of clustering that I'm going to mention that at the very end. Is where you have graphs. So in that case, you have vertices. The vertices now represent the data elements, and there is an edge between two data elements if there is some similarity. So there is no more metric space. It's not encoded. The similarity is not encoded through a distance. It's encoded whether there is an edge or not. So we can think of this as like social networks where each individual in the social network is represented by a vertex, and if there is some relationship, friendship, anything between two members of the social network, there's going to be an edge between the two guys, two persons. Okay, so that's another way to represent a similarity between data elements, and you could try to find dense subgraphs. So basically points that are a lot in common. Okay, a lot of relationship in between. And finding dense subgraph, you can also come up with different ways of modeling it, but that's a very fundamental notion of clustering. And there are various FPT or non-FPT questions related to that, but I'm going to talk about that at the very end only. Okay, so these are the basic motivation for clustering. And for this talk, I'm going to talk about the metric space one. And so for me, the clustering I'm going to talk about is the following. So you get a metric space. So here, gamma is the set of points, delta is the distance. And the distance for now, I'm not assuming anything, right? It's just a metric space. So the distance satisfies triangle inequality, but it doesn't have much more structure than that for now. Okay, so it just satisfies triangle inequality. You could think about the L2 norm, different distances between points, but that's not what I'm going to go into that very soon, but for now, it's like just triangle inequality. The input of the clique clustering problem is a set of clients, which is a subset of points of the metric space, together with a parameter K, which is the number of clusters you want. And the goal is to output K representative of your input, such that you minimize the sum of the distances of the cost from each point to the closest representative. Okay, so it's how well your data is represented by the representative. Okay, so for K-median, the cost is simply the distance between the point and the closest center. For K-means is the distance squared. Okay. So that's the K-median and K-means. These are the very fundamental, like very basic clustering problems. And I'm gonna focus on these guys for the rest of the talk. If there is any question right now, you can maybe ask it in maybe you have to voice it, because yeah, the group chat is not very.
So, yes. People, it's not a question, but people are saying that there's a black triangle on the left top of your screen.
Here?
Yeah, perfect. Yeah, that's better. Yeah.
Okay, good. So yeah, this is the Zoom stuff. Okay, good. So okay, so let me try to move forward. So interestingly, this is a very old problem. This is K-median problem when K equals 1. So let me go to the K equals 1 setting. So this is a problem that dates back to Fermat, and maybe that's FPT because K is like 1. So the simple parameter is K is 1. So no, it's a very fundamental problem. You want to I give you a couple of points in R2, so in the metric space, but this is R2, very simple. And that's a question that Fermat asked. Can you find the point D that minimizes the sum of the L2 distances to this point? So you give you IBC, you want to minimize the sum of distances A to D, B to D, C to D. Okay, and so Fermat gave, or Torricelli maybe gave a solution for the case of 3 points. And if there are more than 3 points, it starts to be hard. So in fact, you can't even express it nicely if you are under L2 norm and so on. So it's a little messy. And you can ask, if I raise this question into high enough dimension. So say I give you like n dimension, n points, n dimension. Can you compute? What is the complexity class of this problem? Right. So it's probably beyond NP, but people don't know exactly what's the complexity. So that's a very fundamental problem. Like for the 1 median problem, we can't solve it exactly in R2 if you don't bound. You allow me to pick points everywhere in the median can be anywhere in RD. So there is a little technical way of going around this problem, which is going to a discrete version, what we call a discrete version. It's not of the problem, where in the input, in addition to the client set and the parameter K, you also get a set of candidate centers from which you have to pick from. Okay, so now you have to. Now, for the output, you need to pick your representative from the set of candidate centers. And now, with this problem, of course, the set of candidate centers becomes part of the input, so it can't be like all R2. I mean, like we expect it to be polynomial size, and so you can, now the 1 median is trivial, right? You can just iterate over all candidate centers, compute the distance to the client set, pick the best one, and that's it. Okay, so now the problem becomes like the 1 median problem becomes trivial. You can solve it exactly, but the difficulty will come from the fact that you are from larger K. But by the way, I think that the continuous version, the non-discrete case where you need to find the 1 median is already interesting. So that's okay. Let me check the group chat. Okay, so no question right now. So okay, so let me move forward. Okay, so now here's a question that you can test your intuition on that question, which is that, is this problem easier or harder? I mean, like, in some sense, I give you, there are two, I mean, like, I want to say yes to both questions in some sense, because it's easier in the sense that now we are not running into the Fermat problem anymore, because, the set of candidate center is given to me. So there is not this real numbers computation that I need to find, for finding the right centers. So somehow it's easier because I know where to pick from. On the other hand, you can say, okay, but it's harder because I'm more. It's kind of more constrained. So I can't locate a center anywhere I want. So in fact, I can maybe have a higher inapproximability. I have more constraints. So maybe the problem becomes I can encode more gadgets. I can enforce to some specific location and maybe encode more gadgets. So maybe it's harder. So and I think and I will see later in this talk that in fact both answers are true. Both, it's both easier and harder. We'll see. In different settings it's harder, and in other settings it's easier. So it's kind of a surprising phenomenon here. Okay. So let's review the exact computations here. So the problem is the K-median problem, where you and the K-means problem when you can locate when I give you a specific set of candidate centers, they are known to be NP-hard even for k equals 2 in if you have enough dimensions, and they're also NP-hard if you have large k in small dimensions. Okay, so that's the other, they are kind of complementary. And it's W2 hard parameterized by k in general discrete metrics. And this comes from a set cover reduction that we'll see later. And I mean, it's kind of a trivial W2 hardness when you parameterize by k coming from set cover. So it's very standard. And for LP metrics, there is an exact n to the kd plus 1 algorithm. So in fact, this algorithm holds for the continuous version as well. So basically, you can enumerate all Voronoi diagrams in D dimension, all size k Voronoi diagrams in D dimension in times n to the kd plus 1. So you can find the exact solution. Assuming you can solve the Fermat-Weber problem, like the problem like for the K-median. For the K-means, the problem is not there because you can always take the mean. This is easy to compute. So it's really coming from the median in L2 that this is an issue. The median in L1 is you can compute exactly. Okay, so that's that. And so more recently, there has been a focus on this kind of fine grain or FPT analysis of these problems. So a couple of years ago, we showed that in fact for the discrete version, you have an n to the omega k lower bound in R4. So even in very low dimensional space, you still get an omega k lower bound under ETH. We showed that you can get n to the square root k in R2, which is not too hard. But again, all this is for discrete. And we kind of left open what's happening in R3. And that's not, I mean, it's still pretty unclear. I don't know what's the right answer. Is it like, it's probably, yeah, so it's in between square root k or k, but I don't know exactly what's the status there. Also for some technical details, we didn't manage to prove a matching lower bound in R2, even though I think that should work. Okay. For the continuous case, there is a D to the D FPT algorithm where this is the value of the optimum solution or the certificate you are trying to ensure. And there is still this open question that, whether you can improve this n to the kd I was mentioning on the previous slide, the exact n to the kd algorithm of Inaba et al. Can you match it with a lower bound for continuous? Or can you get the n to the k plus d or n to the k for any d? That's pretty unclear now for continuous, at least. I mean, this is simpler. Can you get a lower bound of n to the d for constant k, something like that? That's yeah. So these are things. So okay, so let me check the chat, and otherwise you can voice your question if you want. I don't see any question in the chat, so if you have any question, feel free to ask. Okay, so let me otherwise move to a kind of a summary. So there is an exact in n to the dk plus 1. It's kind of ETH type for discrete. We don't know what's happening in continuous. If you parameterize by D, and now I'm adding the approximation ratio, the best known approximation for this setting too. If you parameterize by D, we showed last year, for example, that you can get 1 plus epsilon in time f of D epsilon and polylog n. So that's like FPT in D and n log n and polylog. So that's more or less the best you can hope for, because NPR for D equals 2. So that's the best. No dependency on K. Same thing for the parameter. If you parameterize by K, you get the same answer, which is that NP half for K equals 2, and then you get 1 plus epsilon in time f of K epsilon and polylog n. That's Kumar, Sabharwal, and Sen from 2010. And maybe the general case where you don't parameterize by anything, that's the best known, is like 6.357 and 2.6 for K-means and K-median respectively. And that's Ahmadian, Norozi, Fouad, Stevenson, and Waltz from 2017. So that's for K-means and K-median, and that's the best known so far. So okay, so that's the setting in LP metrics and for this clustering problem. And there is also hardness of approximation in the general case. We showed, for example, last year that you can't really get very strong approximation. So there is this phenomenon that there starts to be an interesting phenomenon if you combine this slide and the slide before, which is that the L1, L2, L infinity metrics, you get some hardness coming from the for the general case, when you want some algorithm that run in both poly K, poly D, poly N, you get some hardness. You can't get 1 plus epsilon in LP metrics. Okay, we get some hardness lower bounds. Okay, so that's even for the continuous case, we get some lower bound of 1.07 and so on. So that's the issue. But if you remember the previous slides, for the FPT world, this is not true, right? For this FPT world, you can get 1 plus epsilon. So there is a little discrepancy, right? If you want poly, you have this you have this hard apex hardness. You can't get 1 plus epsilon. If you move to parameterize by D or by K, you can get 1 plus epsilon. So there is a little gap between FPT. There's the complexity gap between FPT and poly time. And of course, you're going to say, okay, but that's happening for many problems. That if you want FPT, you can get better bounds than if you want poly time. But the thing is that for the general metric space setting, this is not true. For the general metric space setting, the best non-FPT, I mean, the lower bound for FPT is the same lower bound as for general poly KN. Okay, so if you parameterize by K in general metrics, you have no benefit compared to poly. But interestingly, if you move to LP metrics, then parameterize by D or K, then you get a better approximation. Okay, so that's an interesting setting. So okay, so that's the so these are the settings for general metrics. So there is a 9 approximation, and there is a lower bound of 1 plus 8 over E. And there is a 2.67 approximation and a lower bound of 1 plus 2 over E for K-median. Okay, so this is the best known for this case. And that's the gap I was saying, is that if you parameterize by K, you end up with 1 plus 8 over E approximation and hardness, and 1 plus 2 over E and approximation for both K-median K-means. So for K-median K-means. And that's a paper we showed last year. And there's this little gap that I found interesting between LP and general metrics, which basically breaks the hardness, the approximation hardness. Okay, so the LP metric is imposing so much structure than the FPT now has, which is kind of interesting. And in fact, maybe for the side story, when we were designing this in approximability results, we needed to kind of start from a problem for which we knew that if you want to reduce from this problem in general, like the reduction should work in Euclidean space, So the problem should be easy in the FPT world, otherwise you would have a contradiction with previously known results. So in fact, we were inspired by the FPT results to find the right problem to find the reduction here. Okay, so that's the setting for clustering, this little discrepancy between LP and general metrics. Okay, so let me check that there's no question. Oh yeah, LP metric. Yeah, so that's you take some you have some vectors and then you take some norms of the two vectors. So yeah, so you should check the definition. Sorry, I didn't define LP metrics. I should have maybe for this talk, for those who are not familiar with LP metrics, you can think about Euclidean distance. Okay, so like you take your vector in RD and then you take the you take the distance between these two vectors. L2 distance, but yeah, the standard distance. Okay. Okay. Any other question? I guess it's if there is nothing more, I'm gonna move to the next step. And so I think this gives a little bit of reflection. I mean, like, there is this somewhat observation that I just described that 1 plus 2 over E is the best you can do, even if you parameterize by K in general metrics, but you have a 1 plus epsilon approximation scheme if you move to Euclidean space, no matter what's the dimension. And if you parameterize by K. And if you don't, then you again have a harness. And then you can try to reflect what this tells us, right? So is this like a coincidence? Is there more to take away from that, or like is there something else behind? Okay, and I think it's nice to see these clustering problems are set cover problems. In fact, they are very close to set cover problems. They are so close to set cover problems that it's almost like a little variant of set cover. We should just see them as little variant of set cover. And in fact, getting good algorithm for this problem is the same as getting good algorithm for set cover. So let me try to give you why they are so close to set cover. So take a set cover instance. So you have a bunch of sets you need to pick from, okay, to cover some universe U. And now you need to decide whether you can pick at most K sets so that you cover whole U, okay, the entire U, the whole universe. Okay, so now let me start with this. You give me this set cover instance. I'm going to build a K-median instance as follows. I'm going to create a client for each element of the universe, and I'm going to create a candidate set for each candidate center for each set. Okay, and now the distance between the client and the candidate set, a candidate center, is going to be 1 if the elements belong to the set, and otherwise I want to put something very large. Okay. So now the goal is to, if there is a solution for my set cover instance that has K centers, the solution to my set cover that has K sets, then I pick the corresponding candidate centers, and everyone is at distance 1. So I'm just paying the cost of the universe, the size of the universe. If there is no such solution for set cover, then at least one client is going to be paying a very large cost. So, I will be able to see the gap between the two. I'll be able to. So, K-median is in some sense a metric set cover, right? So the question is, if I put this very large to be infinity, then you would have like, you have the goal is to distinguish between U, the cost of everyone paying 1, or everyone but one guy paying 1 and the other guy paying infinity. So, there's a kind of gap. And in fact, that's how you would design harness of approximation for these problems. And let me try to give you a more formal proof of this connection. And we will see how this more formal proof, which works in the polytime world, can help us design FPT algorithm later on. Okay, so we will start from this problem, which is basically set cover, but more useful for clustering problem, which is I give you, the input is a universe and a collection of subset of the universe and a parameter K. And the objective is to cover the maximum number of elements of the universe by picking at most k sets. Okay, so that's the max coverage thing. So it's a little bit like set cover, right? So in fact, it's so close to set cover that the hardness for these problems come directly from set cover. And there is the reduction by Feiger for set cover, the hardness, the log n hardness for set cover implies directly that this problem is hard to approximate within a 1 - 1 over e approximation. Namely, that you can't distinguish between an instance where the optimum solution is 1, you cover everyone, the fraction you cover is 1, you cover everyone in the universe, or you can't cover more than 1 - 1 over e plus epsilon. Okay, so that's the problem we want to work with. Any question on this problem? Looks okay. Okay. So now we start on this problem and we move to the k-median version. Okay. So what we do is what I described before. For the candidates, for the sets, we create candidate centers. For the universe, we create clients. Now, if a point belongs to a set, an element or the universe element belongs to a set, you put distance 1 between the corresponding client and the corresponding candidate centers. Okay. And if they don't belong, if the client does not belong to the set, then you put distance 3. Okay. So that's the very large. Before I said very large, now I put 3. So 3 is not that large, but let me go with 3 for now, and we'll see why 3 is needed. Okay, so let me go with this. So now, if there is if the instance of mass coverage was a yes instance, namely I can cover the whole instance with k sets, then there is this k candidate center such that each client is a distance 1 of a candidate center. So my k-median solution is at most u, the size of the universe. Okay, that's the yes case, not very hard. Now in the no case, it means that there is the max coverage distance is such that for any k subset of candidate centers, at most a 1 - 1 over e fraction of the clients are covered. So they are distance 1 from these guys. And the rest of the client, the 1 over e fraction is at distance 3. Okay, there is no choice. And so the optimal cost of that instance is at least u times 1 - 1 over e, which is the guys that you can potentially cover, plus 3 times 1 over e, which are the guys that are not covered because they are distance 3 from this. So if you sum up, you get that the optimum solution in this value in this for the no instance has that cost at least 1 + 2 over e times u. So this, from the max coverage, you can get this, which is due to Guo and Kula from 99, which tells you that it's NP hard to distinguish between a yes instance where you would have cost x and a no instance for which you would have cost 1 + 2 over e minus epsilon times x. So that's how you get a hardness of 1 + 2 over e for k-median. Any question on that? Looks okay. All right. So what are the ingredients in this reduction? So if a universe element belongs to a set, the distance between the two corresponding elements is 1. Otherwise, it is 3. And why is it 3? It's 3 because of triangle inequality, because you need to satisfy triangle inequality. So in fact, you can't put larger, otherwise the instance you may generate is not a metric instance. So you put 3. And that's how you get this gap. Okay. So that's the thing. And now, of course, you can ask the question, if you impose additional factor on the metric, like, it becomes, you don't have only triangle inequality where you need to put 3, you would have to like Euclidean distance or shortest path metric of a minor free graph or Jaccard distance, edit distance, any distance you would like. How does this hardness evolve? And that's what we try to do in the polynomial time world. And we saw that the hardness, for example, in the FPT world disappears for Euclidean, for example. Okay. But now let me try to use the knowledge we have from this reduction to get an FPT algorithm for the general case. Okay, so that's a result we had last year at ICALC with Anupam, Amit Kumar, and Jason and Weiyong Li. So if we were working in the reduction instance, okay, so if I was working in the instance where 4 points are at distance 1 or 3 from their center, okay, in opt. Okay, so either 1 or 3. Okay, that's easy. Then what we can do is, we can just use the 1-1/(e) approximation for max coverage, because we know that we have the centers. For each center, you can say, okay, these are all the guys at distance 1. Okay, that's my set, and we know how to get log n for set cover. We know how to get 1-1/(e) for max coverage. So if we were really working in the reduction instance, we could get 1 + 2/e. We would be getting 1-1/(e) fraction of the points being 1/e fraction being 3, because everyone is a distance at most 3 from the rest. Okay, so if you give me the reduction instance, then I'm happy. I know how to solve it. Now, how do I move from this reduction instance to a more general instance of K-median? Okay, and that's the challenge. Okay. And note that this challenge is also true in the polytime world. I mean, it's a challenge for both FPT, polytime, fully polytime world. I mean, it's a challenge. Okay. Yeah, so the distances are more diverse, right? So you may have some points that are distant epsilon from some centers, then infinite from the other. You have some kind of huge diversity on the distance. I mean, you can assume up to losing 1 + epsilon factor, you can assume that they are poly, the gap is poly, but you still have a poly gap instead of 2 distances, right? So 1 and 3. It's a big step. Okay. So how to move to this setting? Okay. So now I'm going to describe the algorithm, and there are 3 steps. The first step is using a core set, which is like an approximate kernel, basically, for if I want to translate this into the language of fixed parameter tractability. An epsilon core set is a weighted set of clients, such that for any set of K centers, the K-median cost of the core set client is the same as the K-median cost of the original client, up to losing a 1 + epsilon. So it's a good, you reduce you get a smaller set of clients, but the cost remains the same up to losing 1 + epsilon. So we are happy with it. And what we know is that there exists core set of size up to polylog K, polylog log n, polylog n maybe. There are core set of size poly K, polylog n in general metrics, and you can compute them in polytime. So you just end up with a weighted set of size. But okay, let's go with the step 1. The step 1 is compute a core set. That's polytime. We are even faster than we don't need the FPT time. We can just compute polytime core set. Okay, so that's good. So far so good. I'm not going to dive too much into the core set. I think it's. I mean, I'm happy to talk about it offline. Answer question about that, but it's not. I mean, it's very nice. There are a lot of ideas for computing these core sets, but it's not. I mean, it's not really what's the meat here, I guess. Okay. The second step is to pick among the core set points. So if you have the core set that was of size K, then you can try all possible partitioning. That's K to the K. Of course, here, note that the core set has size K log n. So if you were to try all possible clustering of these K guys, of these K log n guys, this would be K to the K log n, and that's too much. So this is not FPT anymore. That's n to the K. We didn't get anything. So we can't. I mean, it's nice because in some metrics you can get core sets of size K. In which case, then you are done because you can enumerate. But in general metrics, you need to have this log n. So the core set has size K log n, so you can't enumerate anything yet. You still need to do something a little smart. Not too smart because we did it, but a little smart. So among the core set points, you guess the K points that are the closest to the K optimal centers. Okay, so this we call the leaders. Okay, so for each, consider the optimal clustering. For each of the clusters, there is one point that is the closest to the center, and that's the leader of that cluster. Okay, so you want to find the K leaders. Okay, so you know, if you look at the drawing, there is the opt centers. All the clients and leaders are the clients, the core set. Okay, I'm now working with the core set only, and the leaders are the, you know, the clearly the clients that are the closest to the centers. Okay, and so this is what you want to do. You want to guess these guys. So who are they? I mean, of course, there's not that many guess because you know, you have K log n points, and you have to pick K from there. So that's K log n to the K. That's FPT. And now you also want to guess their distance. And you can guess approximately their distance up to 1 plus epsilon factor. And then you don't have that many distances that are there. So it's going to be K log n to the K as well. So remember, we guess two things here, and that's the FPT part of the algorithm. That's the only time where we spend FPT time in this algorithm. We guess the K leaders and their distance to the optimal centers. Okay, that's step 2. Okay, now let's pause at step. There will be a step 3, but I want to pause at step 2 because there is already, like, you can ask me what did we get. Okay, so what do we gain from that? So if you look at the leaders, these are the green points in my drawing. We get the leaders and we get the blue ball. The blue ball are the distance to from the leader to the optimum center. Okay, so we guess basically green and blue. And the red points, they are inside the blue balls. We just don't know where, but they are somewhere inside. Okay, so we have changed a little bit the question, right? If I guess correctly the green guys and the blue balls, now the question, the algorithmic question I need to answer is find the best K centers that are picked from the blue balls so that the cost is not too expensive. Okay, that's more or less the question. And okay, so now how we can, why is it so much better than what we were doing before? Okay, so one answer to this question is to say, okay, let's pick any center in the blue ball. Okay, so I would like to pick the best, but maybe I can't pick the best. Maybe I'm too stupid. So if I'm too stupid, I can just pick any center in the blue balls. Okay, so let's say I pick I pick the yellow guys. They are not the optimal one because, you know, the optimal one are the red guys, but I pick the yellow. And now, is it good in any sense? Okay, and here's the thing is that actually we can show that it's pretty good. In fact, we claim it's a simple, it's a 3 approximation to the problem. Because pick any client. I don't know if you see my mouse, but okay, so pick any client C. Now, note that the distance from C to the red, which is the optimal thing, is some kind of opt C, right? Written on the drawing. And now, what is the cost that this client C is paying in the algorithm? Is the yellow pass, right? And so now let's try to bound the yellow pass. So the yellow pass is at most the red pass plus DI to go from red plus the diameter of the blue, right? Is the red plus the diameter of the blue by triangle inequality. Okay. Now remember that the red is larger than DI, the radius of the blue. The red is larger than that because the green is the leader. So the green is the closest one to the red. So client C is further away than the leader. So opt C is larger than the radius of the blue. So in that case, what I'm paying is opt C plus the diameter of the blue, which is then at most 3 opt C. So in that case, you know, if I just pick any guys in the blue boat, I get a 3 approximation. So if I make the correct choice of leaders and distance guess, I'm getting an easy 3 approximation. That's a immediate thing. Okay. Okay, so we get the 3 approximation. This is not very exciting at first, but now this solution ALG, I'm going to call it ALG in the next slides. We can try to improve it. Okay, and this is where we can try to be smart. Okay, so we can try to improve this solution that is a 3 approximation. So I'm going to promise that we will pick one center in each blue ball, because it's our guess, right? So we need to pick one center in each blue ball. Then by the above argument, we can show that no client C will be paying more than 3 times what it is paying in opt. So each client is going to be paying something which is between what is paying in opt and 3 times what is paying in opt. Okay, so there's now a factor of 3 between what is paying in opt and the worst case if we pick anyone in blue. Okay, is there any question here? Or how do you get the distance? How do you get the distances? Okay, so here's an easy answer to this, how you get the distances. So you can reduce the span of the distances to be polynomial, because you can compute, for example, a constant factor approximation, and now any distance that is smaller than this constant factor approximation divided by n squared or something, or n cubed or something, you can just contract and assume that the 2 points are at the same location. And you know, and any distance that is higher than this constant factor approximation, you can remove. You can just break the instance. So now, you know, the gap between the distance is like polynomial. It's like the span between the smallest instance, the ratio between the smallest instance and the largest instance is like n cubed or something. And then, you know, we can try to round to power of 1 plus epsilon the distances. And then there are like log n distances. And now it's like log n to the k distances that we want to guess. Good. So that's how we guess the distances. Okay. So going back to this, just a very quick summary. We have these blue balls. We promise to pick one center in each blue ball. And for each point, it's going to be at most 3 times what is paying in opt by the above argument here. Okay. So now this is nice. This is very close to what we had before, right? Remember, in the hardness proof, if a point was covered, it was paying 1. If a point was not covered, it was paying 3. Now it's slightly different. If the point is covered, it's paying what is paying in opt. If a point is not covered, it's paying at most 3 times what is paying in opt. So it's very similar, right? It's just like 1, 3 versus opt, 3 opt, but it's very close. So, okay, so now the step 3, which is the final step for this algorithm, is that for each client, you're gonna pay the distance to the leader plus the guess. You start with delta C being the minimum of all leaders of the distance to the leaders plus the radius. Okay, so that's exactly what we had here. It's like the distance from C to UI plus DI. That's what we are gonna, that's how we define delta C. And for any set of centers, we are gonna define a function which is how well, how much it improves the ALG solution. Okay, so we're gonna say that, okay, if you give me a set of centers S, I'm gonna say that the value of S, the gain I'm getting from S, from picking the center in S, is the sum of the distances from each point, each client to the closest center in S, minus delta C. And delta C is basically what you are paying in the naive solution, in the 3 approximation. That's what you are paying. Okay. So think about delta C as what you are paying in the naive solution. And S is your improvement in cost. If you improve S is the improvement in cost over this naive solution if you are taking the center S. Okay, so it's really like the net gain in cost. So you want to maximize improve S so that you get the best possible gain. Okay, so we start from a 3 approximation. We would like to get down to 1 approximation. And so you know that the best solution for improve is opt. So opt for the K-median solution gives you the best improvement. So you would like to find opt to get as much improvement as possible over the current naive solution. This is a little tricky. I mean, you need to think about, you need to kind of take in reverse, backward, right? In the sense that we have a minimization problem, and now we are starting from a bad solution, and we are trying to improve this solution as much as we can. And this is what the improve function measure. So we want to maximize improve so that we get the best improvement and get as close to the best cost as possible. Okay, I hope this is okay. Okay, this looks okay. No question means okay. Okay, so what we want is to find the best S star that maximize improve while picking 1 element in each blue ball, because that's the promise we have made. We have made a promise to pick 1 element in each blue ball. If we don't pick 1 element in each blue ball, then, you know, all hell can break loose. Right? Like, you know, it's a mess. We don't know what's happening. Okay. Okay, so let's try to find the best S star that may maximize the improve. Okay, so now, okay, let's see the reasoning behind all this in equation, because that's going to be more helpful to this. So the final solution that we will obtain at the end of running this algorithm is alg minus improve of the solution that we have chosen. Okay, the solution we'll get at the end, if we pick a set S prime, is going to be of course alg minus improve of S prime. Okay, the best solution for improve is achieve you know, alg minus opt, because it's achieve this. That's the value. The best solution is opt, and it gets you a alg minus opt improvement. So, and what we can show is that improve is a submodular function, so we can get a 1 minus 1 over E approximation to improve. We can't solve improve exactly. We don't know how to get the best solution for improve. So we are going to solve improve approximately. Improve, we're going to get a 1 minus 1 over E approximation to the best solution of improve. Okay. In polynomial time. So again, we don't use FPT here. As I promised, we use FPT only on the second step. That's the third step, we don't do it. So the final solution has cost what? It has alg minus the value of improve. Okay? The value of improve is a 1 minus 1 over E approximation of the best value of improve. The best value of improve is alg minus opt. So what we get is a final solution of cost alg minus 1 minus 1 over E alg minus opt. And what's that? That's 1 minus 1 over E opt plus 1 over E alg. And remember that alg is at most a 3 approximation, exactly like in the reduction. So in fact, what we are getting here is a 1 plus 2 over E approximation, which is the best you can hope for, assuming gap ETH. And I think now it has been improved, and maybe you need a, yeah, okay. So yeah, 1 plus 2 over E to bond is the best. Okay, so is it somewhat clear? Like, let me try to take question here. If voice your question, type your question if there is anything. We just use this improve function to model how much you can improve this naive solution. And this function ends up being a submodular function with a matroid constraints which come from the picking blue balls. And then you want to you can get 1 minus 1 over E. And you know, alg is a 3 approximation. So the best you will get a 1 minus 1 over E opt plus 1 over E alg, and that's 1 plus 2 over E. That's the best. Okay, so yeah, that's 1 plus 2 over E in f of k poly n. And the interesting thing here, I think, is that, you know, only step 2, which is the guessing of the leaders and their distance to the opt centers, is not poly k. That's the thing where you use like f of k. And the rest remains like, you know, poly kn. So, so the main open question here is that, if you could do this second step, which is the guessing of the leaders and of the good blue balls, in poly time, poly kn, then you would get the 1 + 2 over E approximation for the K-median problem, which would be best assuming P versus NP, right? So this is clearly, and there is a good sign to think that this is the right answer also for the poly K, for poly K, poly N case, right? So if everything is poly time, I think a lot of people believe that 1 + 2 over E is the right answer. And then, the only thing that remains here is getting these blue balls or leaders in polytime, or completely other. I mean, you can have a completely different approach, but it seems that that's one of the bottleneck. But that's bottleneck here. Okay, so that's that. And now I'm gonna finish with a lot of open questions that it's that are there. So if you move to the capacitated case where each cluster can have a fixed number of points at most, fixed, which would be like some given number, like each candidate centers has a number of clients that can be assigned to it. Then we also got like the 3 approximation, basically using the exact same approach, except that the third step doesn't work. The third step doesn't work because it's not clear that the function is sum-modular. So you can't just apply it there. So we just stop at the second step, which is the naive step. The contribution we had in this paper with Jason Lee is the computing the core set, that showing that there is a core set for doing the first and second step for the capacitated case. That's what we showed. But the question is like 3. Now we get 3 using this naive approach. Can you go beyond that? And in fact, it's not clear that even in the poly KN world, it's not clear that the hardness is higher than 1 + 2 over E. So in fact, 1 + 2 over E is maybe the right answer also for capacitated case. So so solving the FPT scenario, I think, is interesting. Yeah, lower bound remains 1 + 2 over E. That's coming from the work we had on hardness. So in the L infinity metrics, we show that there is a lower bound of 2 in the continuous case, and that's where continuous starts to be harder than discrete, because in the L infinity, where you can put points anywhere in the L infinity metrics, then there is a lower bound of 2 even for constant number of centers, and there is another bound of 2 in n to the k, but can you do another bound of 2 in f of k poly n? So that's an interesting setting. So in the n infinity continuous case, the lower bound is actually higher than 1 + 2 over E. So it's higher than what we discussed before. Because the set of candidates is arbitrary size. So I mean, like it's not poly size. So you can't just iterate over these guys. You need to find some kind of smart idea to. Okay, here's another interesting question. I think is that what about like other metrics? So let's say, I think an interesting question is the edit distance metric. So because that's used for compressing strings. So they give you a bunch of strings, and you want to find the median of the string. So you want to compute a string that minimizes the sum of the distances to the other strings of your set. So that's a good compression of the set. So k = 1, you just want 1 median. It's a continuous case in the sense that the string is not part of your input. And the best node is a naive 2, because you can pick from, if you pick from your input set, then it's going to be 2. But if you pick but the best known is getting like, I think it's known to be NP hard. I'm not entirely sure it's known to be NP hard, but getting 1 + epsilon approximation would be very, very good for this, like, for getting the edit distance metric in continuous case k = 1. Okay. And I guess that the last slide is this one, is about graph clustering, there has been some recent work on correlation clustering. And I think correlation clustering with a fixed number of centers of clusters. And I didn't go too much into that right now, but I'm happy to take this question offline. I'm trying to work on that because I know that this is a setting that is actually used in practice as well, and of pretty high importance is like getting correlation clustering with a fixed number of clusters. And there are a bunch of open questions which I'm happy to take offline if you're interested. And I'm gonna stop here and take questions if you want. Thank you.
Thank you very much, Vincent. So yeah, questions. There is one question from Monica, I see.
Oh yeah. Oh, okay. Why is this improve a submodular function? That's a good question. Okay, let me try to find a reasonable answer to this. Why is it submodular? Okay, so it's submodular because of the way. Okay, so let me try to come up with a quick answer to this. It's submodular because of the way we define this delta C. So it's submodular because we want to say that if you don't, okay, so you need to be a bit careful to define it in a submodular way. You want to make sure that if you don't pick any center, then the improve is gonna be 0, because you're gonna pay delta C, and delta C, right? So delta C is basically what you would pay if you pick no centers. You want delta C to be what you would pay if you pick no center. So we enforce that by construction. And the delta C is what you want. So if you pick no center, then you get an improvement of 0. So that's the first condition you would need for submodularity. And I guess then if you pick more centers, then you reduce the costs, I think. So that should more or less be this. And I mean, I probably need to check again if this doesn't convince you, but yeah, I mean, it's true that there is a little technicality here to define it properly, but basically the idea is through the use of these leaders, we basically do as if there will be always a center open at twice the radius from that guy. And then if you assume that there's this, then improve is always improve on top of this, so it's well defined. I mean, maybe I should look at the equation again in the paper to make sure that this, but yeah, that's the bottom line.
Doesn't look that there are any other questions. Okay, then maybe we'll stop here, right? So thank you very much again, Vincent. Oh, yes, okay. Yes, oh, yeah. Correlation clustering. Okay, yes.
Oh, yeah. So correlation clustering is this problem where I give you a graph and you have edges that are labeled plus and minus. And there are two variants, like there is the complete graph case where you have all edges, they are either plus or minus, and there is non-complete graph case where there is like some pairs have no edge. And otherwise edges are labeled plus or minus. And then there are two variants of the problem where you want to find clusters so that you would pay a cost that is for all minus edges that are within the clusters, you pay a cost of 1. For all of the plus edges that are across cluster, you pay a cost of 1 as well. That's the disagreement, right? You have disagreement for points that are in the same cluster, disagreement for and that have minus edges, and disagreement for points in different clusters that have plus edges. And then the goal is to say, okay, I want to minimize the disagreement. You can find as many clusters as you want, and you want to minimize the disagreement. And the question here, and we have some preliminary work on that, is to get, if you are forced to pick K clusters, how well can you approximate that? And so there is, and I think, okay, so there is a SODA paper from 2007 by Venkat Guruswamy and Ioannis Jotis maybe, where they show that you can get a 1% approximation in n to the k for the complete graph case. And so it's not FPT, right? It's n to the k. And the question we are looking at right now, and it sounds plausible that in fact you can get 2 to the k poly n. And that starts to be interesting because in practice, you may actually be willing to use such heuristics. And for the, so that's for the complete case, complete graph. And for the non-complete graph, the problem is much harder because in the polytime world, there is no constant factor. And in the FPT, I think it's not known whether there is a constant factor or not. So in fact, presumably you can get like 2 approximation or something for in f of k poly n for the correlation clustering problem mentioned, and yeah, that's and we've plus or minus edges and also sometimes non-edges, and non-edges give you cos 0, so that's the thing. Yeah, so I'm not sure about the, okay, so I'm saying the chat, so edit distance problem you mentioned and closest string, this is like, yeah, maybe there is some connection there. I'm not totally sure about I'm not very familiar with closest string, so yeah, maybe that's the, yeah, maybe that's the thing. Yeah, maybe it's a K center versus K median. Yeah, I'm not 100% sure. Yeah. I think edit distance even over a small size alphabet is not very clean. It's not. I mean, it's not very clean in the sense that it's not known whether you can do like 1 median efficiency. So these are, I think this is a pretty interesting question.
Okay, maybe it's time to say thank you and say goodbye. And
yes, thank you very much.
Someday. Yes, thanks a lot. Bye. Bye.
Bye. Thank you very much.